Today I'm going to start talking about how to discharge the RL circuit without a source. So basically we want to see if we have a inductor and we charge it and then we disconnect the battery from that or the source from that, how that transient happen from that the inductor is between being fully charged to completely discharged. So assume we have a circuit like this. It's going to be a source and it's going to be the R1, and then we have a key, and we have an inductor sitting here, and then parallel to that we have a second resistor like that. And it's going to be, and it's the L, and it's going to be R2. So before the times of assume that in this case when we have it is already the key is closed for the t before 0. So when it's closed for the t it becomes 0. So this inductor is become fully charged, and and eventually start to behave like an short circuit. So it take a while to be fully charged, and after it's fully charged it behave like circuit. After it's fully charged, assume at t0 we actually go ahead and open the key. So for t less than 0 the key is closed. We know that for t less than 0 key is closed, and at t equal to 0 key is open. So we open the key at t0 or so assume at t0 we open the key, so I'll go ahead, so it's opened at t0. So by the time it's open, the inductor is fully charged. I want to see how we can solve that. So I would go ahead and say for let's put it here. Well, let's put it down here. I can say that for t is larger than 0, when we open the key, when we open that, basically this left part of that circuit is not doing anything because it's open, so no currents going there, nothing happened there, so there's nothing goes there if we open it. So if I open it, what for t is larger than 0, the key is open, then what we are gonna have is only this right part of the circuit. So this is what we are gonna have. We have the fully charged inductor, and then we have the resistance connected to that. This is the part of the circuit that actually does something. The left part, it doesn't do anything. So this is a fully charged inductor. When we open the key at t0, the energy in this inductor is going to be dissipated through that the resistance we have here. So there are going to be current here, and it's going to be dissipated. All the energy inductor is going to be dissipated here. So if I go ahead and write the KVL for this one, if I write the KVL in this loop that I have here, basically what I have is going to tell me that the voltage in the inductor plus the voltage in the resistance should become zero. So it's a single loop that we have it. And if I go ahead and replace this, the voltage in the inductor with the L, the inductance, the DIT, um, DIT over DT, and for for the resistance, right, the Ohm loss is going to be IR. So basically it's the I, which is time dependent, times R2. This is going to be 0. So this is going to be our equation. So we know this the differential equation, we have it, and we need to solve it. And we know that we talked about it, the solution for this, if I call this, so this is going to be our equation, and the solution for this equation is, it has the form of the k e to the power of we can write it st as we write it before, or we already know that by now that's going to be k to the power of e to the negative t over tau. So it's the, so this is the solution for this one. And and remember, up to this point we had it, so when we get to this point we have two steps to solve it. The first step is just go ahead and put this solution in the original differential equation, and if you go there, put it there, you can calculate the unknown. And the second part is that you can go ahead and do the, as I said, use the initial condition to solve it. So the first part is that we're going to put this equation into the so this is the solution. So basically substitute 2 in 1. This is the solution, and because it's a solution, should satisfy the equation. So basically if I replace that, it's going to be L d over dt, and it's going to be k to the more negative t over tau. Oh. And plus it, it's going to replace it with the k e to the power of negative t over tau. So it's and then it's going to be, so this is the I, and it's going to be times R2, and this is going to be 0. So if you do this equation and solve it, eventually it's going to give you the k is going to comes out at, sorry, the tau is going to comes out as L over R2. And then so this is what else. So this is very simple equation. Just go ahead and solve it, and you will eventually you will get this value. Then when we have the tau, we need to go and find the k. To find the k, we have to go ahead and use the initial condition. So at t, exactly at t is 0, see what's happening. So when exactly at t0 is that this one is line connected to this circuit, we know that. So for t less than 0, we know that that the key is closed. So this is what we are going to have. So this circuit is going to be like this. So we have the battery connected to that, and then we have the R1, and then we have the key, which is closed. And then we have this capacitor, which is connected to the battery for a long time. Because it's connected to the battery for a long time, let me draw that better. So it's the key, and the key is closed. So we have that because it's connected to the battery for a long time. It behave like a short circuit. It basically behave like as a single wire. So it's just like we replace that with a single wire, because we know that after a very long time, if the inductance is connected to the battery, it behave like a short circuit. And then we have the R2 sitting here. So it's the R2. So because that part, that a capacitor, that inductor behave like a short circuit, basically no current goes through the R2 for the T is equal to 0. So all the current goes in this case goes through the short circuit, or through the I would say the capacitor. So I would say that all the I, nothing goes to the R2, so all the I goes here. So in this case, so it's gonna be a very simple circuit. So I can draw for this circuit, I can say that I at T, just right at T is 0, so at T 0, um, uh, is based, well, let's write it the other way. So I can write it for this circuit, simple circuit, I can write the Ohm's law. So at T is equal to 0, I can say that the V is the Vs, and the I is the I at T is equal to 0, and the R is just R1. So the I at T is equal to 0 is going to be the Vs divided by R1. So this is our initial condition. At the time that we want to open the key, we know this is the current goes through the inductor. This is that current goes through the inductor at the T is 0, so in initial time. Now that we know what's happening here at the initial time, we can go ahead and substitute in the initial condition substituted in equation here in the solution in order to find the k. And if you I go ahead, so let's go to the next slide. So I know the solution is I is k e to the power negative t over tau. So that's the solution that we have. Let me make it it. This is the solution, and we know that at I at t is 0 is Vs divided by R1. And also we know that and we know also the tau is going to be from the previous is going to be so if I just use these together, substitute them, then I know that the I test is going to be Vs over R1 is going to be the k, and it's going to be e to the power of negative 0 divided by tau. So this term is basically 1, so I know that the k is going to be the Vs over R1. So substitute k and tau in the general solutions, so the it is going to be the K, which is going to be Vs over R1 e to the negative t divided by tau, which is going to be L divided by R2. So this is going to be the solution for the discharging. So if you have a discharging condition, if you have a discharging inductor, this is a solution for that. This is how it's going to be discharged. If you want to know the voltage in that also, for example, if you are asked what's the voltage in discharging condition, so we know that the voltage in the capacitor is just di over dt. So you can just simply go time your sales as capacitance times the derivative of this term, so d over dt of that Vs over R1 e to the power of negative t over L over R2. And let me fix that, so it's the V sub S. So it's a V sub S. And if you do the calculation here, eventually what you are going to get is going to be negative L Vs divided by R1, and it's going to be tau e to the negative t over tau, or which the tau is L over R2. So you can solve it like that. You get the equation for this condition. So again, if I go back again in the previous slide, so all we wanted to do very quickly is that we fully charge an inductor, and after we fully charge an inductor by connecting it at the t0, we open the key. At t0 we open the key. So after we open the key, this is what's going to be. So we have the inductor connected to the resistor, and the energy stored in that inductor is going to be released and dissipated through that resistor. So we want to see how that current or the voltage in this transient condition would be. So we write for example, for the current, we write the current equation, and we find the solution for that differential equation. In two steps, the first one, that we put this solution into the equation, it should satisfy it, so it gives us the tau value. And then we go ahead and we find the initial condition, and we put the initial condition in the solution, and that is going to give us the k. And then when we substitute them both in the solution, this is what we are going to get for the I, and this is for the t in case that we need the q. So if I want to plot these current and the voltage in discharging transient, it's going to be look like this. So if I have the it's going to be the voltage, so the current, first I draw the current, and then we have the voltage. See how they behave. So voltage is going to be relatively the same. So for the current, as we know, it's at the when the key is still closed and there is a current go through that, and we know that it's going to be the initial current of that Vs over R1 going through the circuit, and as soon as we we open the key, the current in the inductor is gonna drop through the transient condition until it's completely discharged and becomes zero. So it's gonna lose all the energy it has in that. Same, we know that the voltage in that at the beginning, the voltage in the capacitor is when it's fully charged is we find is going to be negative L Vs divided by R1 and tau. And then as soon as we disconnect, we open the key, so it's gonna lose the energy. So the voltage is gonna again lose its voltage throughout the transient until eventually it's becomes zero. Draw it. So it goes through the transient and it goes through eventually to zero and lose all the voltage it has.